Welcome back to Chapter 4 of Principles of Mathematical Analysis. So far we have studied continuous functions and the beautiful ways continuity interacts with compactness and connectedness. In this short but important section, we turn the question around and ask, when a function fails to be continuous at a point, what does that failure look like? It turns out that not all discontinuities are alike. We will introduce one-sided limits, use them to sort discontinuities into two clean categories, and then walk through 4 carefully chosen examples that show how wild a discontinuity can get. Let's begin. Here is the plan. We start with motivation. Why we bother classifying discontinuities at all. Then we define the right-hand and left-hand limits of a function, the basic tool for the whole section. With those in hand, we define the 2 kinds of discontinuity, the simple ones of the first kind and the wilder ones of the second kind. We then study 4 examples in detail and close with a summary of what we have learned. Up to now, our whole focus has been on continuity, where a function is continuous and what good behavior that guarantees. We proved that continuous functions preserve compactness and connectedness, and that they attain their maxima on compact sets. But every theorem about continuity invites the opposite question. Now we ask the reverse. Suppose a function is not continuous at some point. What exactly goes wrong there? A point of failure is called a discontinuity. As we will see, failures come in very different flavors, some mild and easy to describe, others genuinely chaotic. Our goal in this section is to build a vocabulary for these failures. We will split discontinuities into 2 types. The first kind, also called simple discontinuities, which are tame and well understood, and the second kind, which are everything else. The key tool that makes this classification possible is the idea of a one-sided limit. So let's define that first. Let's recall what continuity at a point means. A function is continuous at x if, as t approaches x, the values of f of t approach f of x. In limit notation, the limit of f of t as t goes to x equals f of x. So a function is discontinuous at x precisely when this breaks down. Either the limit exists but does not equal the function value, or the limit fails to exist in the first place. To tell these cases apart cleanly, we need to look at the function from each side separately. Here's the intuition before the formal definition. On the slide, you see a horizontal axis labeled t, with the point x marked by the dark dot in the center. The idea is to study the function near x by approaching from one side at a time. On the left, the blue dots march steadily rightward toward x, and the shaded band deepens as they close in. The orange arrow points the way. As these inputs creep toward x from the left, the outputs settle on a value we call f of x minus the left-hand limit. On the right, the red dots do the mirror image, and their outputs tend to f of x plus the right-hand limit. Why bother splitting the approach in 2? Because, as the labels hint, these 2 one-sided limits need not agree, and either one might fail to exist at all. That single fact is what the rest of the section is built on. Let's make it precise. Here is the official definition. Let f be defined on the open interval from a to b for a point x with a less than or equal to x less than b. We say f of x plus equals q. If the following holds, take any sequence t sub sen lying strictly to the right of x inside the interval that converges to x. Then the values f of t sub n must converge to q. The word every is essential. No matter which sequence approaching from the right we pick, we must always land on the same limit q. The left-hand limit f of x minus is defined the same way, except now the sequences come from the left, between a and x. This is just the sequential definition of a limit, restricted to one side. This observation ties the one-sided limits back to the ordinary limit. At an interior point x, the full two-sided limit exists if and only if both one-sided limits exist and are equal to each other. When that happens, their common value is the limit. This makes sense. Approaching from either side has to give the same answer for a genuine limit to exist. This little equivalence is exactly the lens we will use to classify discontinuities. The whole game comes down to asking whether f of x plus and f of x minus exist, and whether they match each other and the value f of x. Now the central definition of the section. Suppose f is discontinuous at a point x. We split into two cases based on a single question. Do both one-sided limits exist? If both f of x plus and f of x minus exist as honest numbers, we call this a discontinuity of the first kind, or a simple discontinuity. If at least one of the one-sided limits fails to exist, it is a discontinuity of the second kind. So the entire classification hinges on the existence of those two one-sided limits, not on their values. Let's see what the simple case can look like. When both one-sided limits exist, there are exactly two ways the function can still be discontinuous. The first is a jump, shown in the left panel. The graph sits at one height coming from the left, the solid blue dot, then leaps to a different height on the right, the open red dot. The dashed lines carry each of these heights across to the vertical axis, where they are labeled f of x minus and f of x plus. So you can see at a glance that the two sides land in different places. For a jump, the actual value f of x does not matter at all. The mismatch of the two sides already forces the discontinuity. The second flavor is a removable discontinuity in the right panel. Here both sides agree. The graph approaches one common height from both directions, marked by the open dot, but the function value itself, the solid dot floating above it, sits somewhere else. It is called removable because you could repair it in a single stroke. Just redefine f of x to be that common limit, and the function becomes continuous. Both of these are discontinuities of the first kind. Let's gather the whole classification into one tree. At the top sits the starting point, a discontinuity at some x. It immediately forks into two branches. The blue branch on the left is the first kind, the simple discontinuities, defined by the condition that both one-sided limits exist. It in turn splits into the two leaves we just studied, a jump, where the two sides disagree, and a removable discontinuity, where the two sides agree but differ from the function value. The red branch on the right is the second kind, where at least one one-sided limit is missing. Its leaf is labeled wild oscillation, the behavior we will meet in a moment. Notice the whole tree is driven by just one yes or no question at each fork. So the scheme is genuinely simple. Keep this map in mind, because the four examples coming up are nothing more than instances sitting at its various leaves. Our first example is the famous Dirichlet function. It equals 1 at every rational number, and 0 at every irrational number. Now ask for a one-sided limit at any point. As we approach from the right, we keep hitting both rationals and irrationals arbitrarily close together, so the values keep bouncing between 1 and 0 and never settle. That means f of x plus simply does not exist, and the same goes for f of x minus. Since the one-sided limits fail to exist, this is a discontinuity of the second kind, and it happens at every single point of the real line, a maximally bad discontinuity. The second example is a clever variation. Now f of x equals x when x is rational and 0 when x is irrational. Consider the point 0. As t approaches 0, the rational branch gives t, which goes to 0, and the irrational branch gives 0 outright. So both kinds of points produce values heading to 0, which is exactly f of 0. Hence f is continuous at 0, but at any other point p, the rational values cluster near p, while the irrational values stay at 0. So the function again oscillates, and the one-sided limits fail to exist. Every point except 0 is a discontinuity of the second kind, one single point of continuity in a sea of chaos. The third example is concrete and piecewise. On the first piece, f of x is x plus 2. On the middle piece, it is minus x minus 2. And on the last piece, it is again x plus 2. Let's check the point 0, which is where the middle and last pieces meet. Coming from the left, we use minus x minus 2, which approaches minus 2 as x goes to 0. Coming from the right, and at 0 itself, we use x plus 2, which gives 2. So the left-hand limit is minus 2, and the right-hand limit is 2. Both exist, but disagree. That is a jump, a simple discontinuity of the first kind. Everywhere else, the formula is continuous. Let's see the graph. Here's the picture. Reading left to right, the first two pieces connect smoothly, forming a peak at x equals minus 2 with no break there. That corner is still continuous. Then watch what happens at x equals 0. The graph slides down to the open red dot at height minus 2, the left-hand limit. But the next piece starts up at the solid dot at height 2, which is both the right-hand limit and the actual value f of 0. The burnt orange double arrow marks the size of the jump, a gap of 4 units. Both one-sided limits exist, they just refuse to meet. This is the cleanest possible example of a simple jump discontinuity. Our last example is sine of 1 over x, with the value patched to be 0 at the origin. As x gets close to 0, 1 over x races off to infinity, so the sine oscillates faster and faster between minus 1 and 1, infinitely many times in any tiny interval around 0. The values never approach any single number, so neither the right-hand nor the left-hand limit exists. That makes 0 a discontinuity of the second kind. Away from 0, sine of 1 over x is a composition of continuous functions. So by the composition theorem, theorem 4.7, it is continuous everywhere else. Let's look at how dramatic this is. And here is the graph. As you move toward the center from either side, the red curve compresses into an ever denser band of oscillations, sweeping between the two dashed lines at height 1 and height minus 1 without ever resting. Those dashed lines are the envelope, the band the sine can never leave. The shaded strip down the middle marks the trouble zone right around 0. No matter how far you zoom into it, the picture looks just as busy, because the curve crosses every height between minus 1 and 1 infinitely often there. The blue dot at the origin is our patched value of 0, but the curve around it never settles toward any single height, so that dot is not the limit of anything. This is the visual signature of a second-kind discontinuity, not a jump, not a hole, but genuine refusal to converge. It is a striking contrast to the clean jump of the previous example. Let's gather what we learned. The fundamental tool of this section is the one-sided limit, the right-hand limit f of x plus and the left-hand limit f of x minus describe how the function behaves as we approach x purely from the right or purely from the left. Everything else was built on these. Using one-sided limits, we classified discontinuities. A discontinuity of the first kind, also called simple, is one where both one-sided limits exist. It comes in two shapes: a jump, where the two sides disagree, and a removable discontinuity, where the two sides agree but differ from the function value. These are the tame, well-behaved failures. Everything else is a discontinuity of the second kind. At least one of the one-sided limits fails to exist. The Dirichlet function and scene of 1 over x gave us vivid pictures of this, oscillations so violent that no one-sided limit can form. These are the wild discontinuities. With this vocabulary in place, we are ready for the next section on monotonic functions. There we will prove a remarkable fact. A monotonic function can only have discontinuities of the first kind, the simple jumps, and moreover, it can have at most countably many of them. The wild second-kind behavior we saw today is simply impossible once a function is monotonic. That is a perfect illustration of how today's classification pays off. See you in the next section.